We're about to learn how to find the area between two curves, right? It's a simple formula. You're just going to go top curve minus the bottom curve. And if you use that, it's always a dx problem. So those numbers will be x's. Or sometimes we won't have a clear top and a clear bottom, but we'll have a clear right side of the area. We'll have a clear left side of the area. So we'll go right curve minus the left curve. If you go right minus left, it's always going to be a dy problem. And those numbers attached to the integral will be the y that take you across that bounded area. So this will go like left to right, use the x's. This will go bottom to top, use the y's. The reason that formula works, right? If I want the area between these two curves right here, if I integrate between f of x, like we learned before, that integral gives you the area between the curve and the x-axis. So that'll be all of that. And if you integrate g of x, that bottom curve, that gives you between the curve and the x-axis, right? Well, you don't want that. You want to subtract out that bottom portion. You don't want any of that. You just want the stuff that's in between. So it's this whole integral minus out that stuff that you don't want. That'll give you the area between those two curves right there. So that's what we're talking about, top curve minus the bottom curve. So for each one of these, we're going to follow these few steps. You're going to draw your bounded area. So I don't care if you use the graphing calculator, but I want you to model what I'm showing you for the notes. I want you to draw the two graphs, use the graphing calculator, jot that down real quick on your paper, and we're going to find the intersection points. We'll set them equal to each other, find the intersection points there, but just get that graph down on your homework paper, label your points on there. That'll help us out for the future AP review as well. And we're just going to set up top minus bottom or right minus left, integrate it, and get our answers right there. The beauty of this formula, you don't have to worry about is the portion of the graph above or below the x-axis. If you set up top curve minus the bottom curve properly, it will give you the positive area answer that you're looking for right there. All right. So for example, if you integrate just g of x in between a and b, you're going to get a negative answer, right? But if you set it up as top curve minus the bottom curve, your top curve is y equals 0. Your bottom curve is the g of x. So if you go top curve minus the bottom curve, 0 minus the g of x, your integral of g will get you that negative answer, but you'll have 0 minus that negative number, and that'll turn into plus a positive, and it'll always give you that positive area answer. So you don't have to worry about is the graph above or below the x-axis. You just have to know which is the top curve, which is the bottom curve, or which is the right and the left, and then you're going to be good there. Okay, so if we give you several examples here, let's just talk through this handout real quick. I give the two curves, so you find the area between those two curves. You're going to graph it, use your graphing calculator, or just do that one in your head there. You kind of should know what a lot of those are anyways. And then the graphing calculator as well, if you use the trace button, if you hit the trace button and put your cursor like on that top curve, it'll show you which curve is your top curve. So you don't even have to, but you know that's your x squared graph, that's your line, you know that's your top curve. So you're going to set up top curve minus the bottom curve. Now when you go minus the bottom curve, you're minusing that whole thing. So that whole thing's got to be in parentheses, right? So just be careful with that. Minus the whole thing as one unit, distribute the negative. There's a function we're integrating. Now let's talk about how to get these numbers attached to integral. They won't always be nice numbers, but those are the intersection points right there, okay? As you look at the graph, if this is a dx problem, all the top minus bottom curves are all dx problems. So you gotta go left to right, the x's that take you across that bounded area right there. Now to find the intersection points, what we can rely on is taking these two equations and setting them equal to each other. Do some basic algebra, you're gonna get this 0 and the 3, and then you're going from x equals 0 to x equals 3. Now on a dy problem, we'll go bottom to top. We'll go from like 1 and we'll need to figure out what that highest y value is right there. But right now, we're just, everything's in terms of x's. So we're going to go left to right, go use the 0 and the 3 right there. All right, so this is just another example. I give you the equation. You're going from x equals 1 to x equals 5. Your top curve is that. Your bottom curve is just the y equals 0. So there's just your normal integral. Plug in the numbers, get the answer, okay? What I want to show you on this example 5 here, if you graph y equals sine of x in between negative pi and a positive pi, you can graph that in the graphing calculator. You can hit the window button, make this your x min, make that your x max, and it'll give you just that portion that you want there. Now, if you needed to, when that top curve changes, sometimes you can't do that with one single integral. You could do two separate integrals here. I can actually use one single integral on this one because it's symmetrical. So if you're going to do two separate integrals, if you just integrate between negative pi and pi of that sine of x, you're going to get 0. We don't want 0 answer right here. We want what's the area of those shaded regions. So you could do two separate integrals. Your top curve here is y equals 0, your x-axis. So you can go top curve minus your bottom curve between negative pi and 0, plus the integral between 0 and pi of your top curve minus your bottom curve sine of x minus 0. Or here's what I always do. When I clearly know that that's symmetrical, I like to stick with the positive numbers. I'll integrate between 0 and pi, top curve minus the bottom curve, and then just double that, right? So that's the quickest way. That's why looking at that graph is very important that we have that down, and then you could just integrate it, plug in the numbers right there. So we could do symmetry sometimes. Let's talk about the two scenarios of when I would need to do a dy problem, okay? Some of the problems, the last couple in your homework is going to say this. That's the same thing as saying x equals that, where I don't have y equals stuff in terms of x's. So if everything is in terms of y's, and I can't even solve this, I can't even get that y, like if I have x equals y plus 5, I can subtract 5 from both sides and get y equals x minus 5, no problem. I can't solve this first equation for y equals something in terms of x and do a top curve minus a bottom curve right there, okay? Also, when you graph these two equations, you clearly have a right side of that area and a left side of there. That's on the right side is the curve, the left side is the curve. This is a right curve minus a left curve scenario right there. Now, graphing calculator doesn't graph x equals 2y minus y squared for us, right? We have to be able to do that by hand, okay? So to do this by hand, if I give you y equals x squared, opposite of b over 2a is going to give you the x coordinate for that vertex. But if I have x equals y squared, when I do that opposite of b over 2a, that's going to give us the y coordinate for that vertex. So here's what I can do to graph this thing, right? When I have a quadratic, first of all, this is just y equals negative x. So that's just that linear function there. But I'll do the opposite of b over 2a. And please practice this. A lot of times people bomb this stuff on the test. They don't obviously didn't practice it or listen to me right now. Please practice this. But the opposite of b over 2a, that's going to be like 1 over 2. I'm sorry, that's going to be just your b is that positive 2, your a is at negative 1. So the opposite of b over 2 is just negative 2 over 2 times negative 1, which is 1. That's normally the x coordinate for the vertex, but when you have the y squared, that's going to be the y coordinate for the vertex. And then you want to choose numbers around that 1. So eventually these x's weren't there. Once I got that 1, that's like my starting point. I choose a couple numbers above there, like 0 and 2, and a couple numbers below there, like negative 1 and 3. So you can go like 0, negative 1, and then 1, 2, and 3 there. I don't know why I did a slightly different order there, but just get those numbers in there and then take those numbers for the y, plug those in place for the y, and get your corresponding x's. And then you could just plot the points and connect the dots. But you should also know x equals y squared is like a parabola that's going to open to the right. X equals a negative y squared will be a parabola that's opening to the left there. But we should be able to practice plotting those points and connecting those dots. And then when you do right curve minus left curve, see how the curve is on the right side of that thing? That's your parabola. That's what my right side. So that's what I'm doing, right minus left using the dy problem. So my curve is on the right minus the left there. So it's just, this is x equals that, x equals that. So it's right curve minus the left curve. So it's that minus the negative y plus a positive y. Have an easy integral. Yeah, really easy integral is this section there. When you use the numbers attached to your integral, since it's a dy problem, take the two equations, set them equal to each other. That gives you your y intersection points right there. You could plug them back in to get your x's, but on a right curve minus left curve on a dy problem, it's bottom to top. What's your lowest y value, what's your highest y value? You're going from 0 to 3. That's why I'm using 0 to 3 right there, and then easy integral right there. Here's another scenario where we need to use the right curve minus the left curve. I can get this equation. This is y equals 1 over x, right? So you're thinking, oh, I'm going to do top curve minus the bottom curve. But when you graph y equals 1 over x, you get this curve here, and you're going, use all sides of the fence. Don't make up your own bounded area. X equals 0 is the y-axis. You got y equals 1, y equals 5. Don't just make up your own area over here, right? Use all parts of the fence. When they give you 4 different equations, use all parts of that fence. That's the bounded area that we're looking at right there. Now, if you try to go top curve minus the bottom curve, it's not really what you want to do here, because your top curve, you got like 5 minus 1 here, and then over here you got the curve minus 1, and so you got two different things there. Why you ain't gonna want to do two different things? Because sometimes that's gonna be impossible to do. You're gonna need like another intersection point right there. Don't make it complicated, right? If you look at this graph, and that's another reason why this graph is important, this is clearly the right side of that plateau everywhere you look, right? And this is clearly the left side of that plateau. So instead of doing two separate things, you want to do one integral here. Just go right curve minus a left curve. Now, once you decide it's a right curve minus a left curve, it's always a dy problem, which means you got to have everything in terms of y's. And so that's why I took that equation. I got x equals 1 over y. There's the right equation, x equals 1 over y. minus the left equation is the x equals 0. And then since it's a dy problem, bottom to top, use the y's that take you across that bounded area, and then you just integrate that, plug in your numbers, good to go there. All right, got a little, oh man, I want some tacos right now. Get some queso, get some salsa, get the chips. Man, that's what's nice about going out to eating tacos, man. They always give you that chips and dips, get some salsa, get some queso going. Stuff is delicious, man. I like when they like double wrap the tortilla too, man. Keep that taco nice and keep all those toppings in there really well. Last thing I want to talk about is kind of similar to what I was mentioning here. If you got a couple different equations here, you can't, if I say what the area of these camel hump looking things are, you can't just integrate. When the top curve changes, you can't just integrate from A to B. It's not going to give you the area of each one of those. It's going to give you this net result type of thing. So you don't want to do that. So when the top curve changes, you need to do more than one integral. Well, here the top curve changes, but I didn't need to do, I could actually do one integral because it was symmetrical, but this one right here isn't really symmetrical, right? You just got two different curves there. So what you have to do is just do two separate area formulas, top curve minus the bottom curve. So that's why it's important to graph it. Use that graphing calculator, hit that trace button, see that this is your top curve, or see that this is your top curve, and then you can go top minus bottom between A and B, between B and C. So sometimes we need to look at that graph, and if that top curve doesn't change, we could always do it one integral like we did this guy right here. But if that top curve changes, you're going to need to break it up and do that in a couple of separate integrals there. So the nice thing is easy integrals this section, easy integrals this the whole entire chapter really. Until we get to that next chapter though, whoa, yeah, that's going to be some intense stuff there with the integrals. But really, we're just practicing how to do the areas and then get good at this because we're going to do volumes in the next couple of sections there. Those will be a little bit more intense. But if we get practice with all this stuff here with the graphs and everything, we'll be good there. But usually this is a pretty easy, doable section for us there.